care that much, what it physically is. Okay, it could be an electron that has, where 0 is its ground state and 1 is its first excited state. Okay, it could be an atomic nucleus where 0 means it's spinning clockwise, 1 means it's spinning counterclockwise about some axis. And there are many other examples, just like a classical bit. Could be, we physically instantiate them in our computers by voltages, in transistors. Okay, but there are many other things that, that could, even the position of an abacus bead that could represent a classical bit. Okay, so it is with a qubit. Okay, now, if I have 2 qubits, so say like 2 particles, whose spins I'm keeping track of, the rules are very unequivocal that I cannot just assign amplitudes to each qubit separately from the others. Instead, I need an amplitude for every possible configuration of all of my qubits together. Okay, and this is really crucial. So if I have 2 qubits, I now need 4 amplitudes. I need an amplitude for 0, 0, and for 0, 1, and for 1, 0, and for 1, 1. Okay, every possible 2-bit string. Okay, and so in particular, I could have a superposition of 0, 0, and 1, 1, right, which would have the property that if I measure one of the qubits and I see that it's 0, then immediately I know that the other qubit is also 0. And likewise, if I see that one of them is 1, the other one is also 1. Okay, you've heard of entanglement. That's what entanglement means. Okay, so it's the sort of the quantum version of correlation. Okay, and again and again, for the last 100 years, people get excited that doesn't this mean that I can send a message faster than light? And again, for 100 years, it has to be explained to them, no, it doesn't mean that, okay? Because, you get to measure, but you don't get to choose the outcome of the measurement, right? And that's what would be needed to actually send a message faster than light. So this actually upholds the letter of, Einstein's relativity, even though it is in a weird kind of tension with it. And you can do experiments with entangled particles whose results you could not explain without the entanglement. And if you've heard of the Bell inequality, which was this huge discovery from the 1960s, that's what that is about. Okay, but now where we really get excited in quantum computing is when you have not just 2 qubits, but a lot of qubits. Okay, why is that exciting? Well, if you have 3 qubits, now we need 8 amplitudes to keep track of its state, right? For 0, 0, 0, for 0, 0, 1, and so forth. If I have 50 qubits, I need 2 to the 50th power amplitudes. Okay, that is, I mean, you can fit that on, the biggest supercomputers in the planet, but you really do need something like that. Okay, if I have 1,000 qubits, now I need 2 to the 1,000 amplitudes. Okay, that is way more than I could write down in the whole observable universe, even if I used like every atom to store another amplitude. Okay, so quantum mechanics has been telling us, for a century, this is right there in Schrodinger's paper from 1926, that, just to keep track of what 1,000 measly particles are doing, in some sense, nature, off to the side where we never see it, must be maintaining a scratch paper with 2 to the 1,000 power parameters in it. Okay, more than would fit in the whole, visible universe. And every time something happens to those 1,000 particles, nature has to cross off everything in that scratch paper and replace it with new parameters. Right? That is a staggering amount of work for nature to be going to. Chemists and physicists have, of course, known this for generations. They've known it mostly as a practical problem. Right? Okay, if you're trying to solve, quantum mechanics to understand, some relatively complicated, even a fairly simple molecule, even the H2O molecule, for example, right? Or even, fairly simple atoms, right? You have this giant number of amplitudes to keep track of. This is why people, use some of the best high-performance computing in the world for simulating quantum mechanics. And even then, they can't do everything they want. They can, they often have to resort to heuristics and tricks and approximation methods that don't always work. And so it was not until the early 1980s that a few physicists, most famously Richard Feynman, if you've heard of him, David Deutsch, started saying, look, if nature is giving us this computational lemon, why don't we make lemonade out of it? Why don't we build a computer that itself would be made of qubits, that itself would take advantage of this exponentiality of amplitudes and of entanglement and of interference among the amplitudes. Okay, but of course, they immediately face the question, well, supposing that you built that quantum computer, what is it good for? And at the time, they really only knew one answer. It's good for simulating quantum mechanics itself. Right? And that's kind of obvious. And yet, 45 years later, we're still struggling to improve over that answer. We've had a few successes, as I'll tell you about. So now we can really get to the heart of how a quantum computer would give a speed up and how it would not. Okay, and now, if you read pretty much any popular article written about quantum computing for the past 30 years, okay, they say something that sounds, irresistibly good and that anyone can understand. The only problem is it's wrong. Okay, what they all want to say is a quantum computer is just a computer that can try every possible answer in parallel. right? Classical computer, just has to try, each one at a time because a bit has to be either 0 or 1, but a qubit can be 0 and 1 simultaneously. And that means that you get to try each answer in a different parallel universe and then just magically pick the best one, right? Now, like if that was how it worked, like that, that would certainly change the world, right? That would, but that might sound, there might be something in the back of your mind, like, isn't that too good to be true? So here's the